Okay, so this presentation of the paper on FixP membership via convex optimization, games, cakes, and markets. And it's a joint paper with Aris Filos Rasikas, Christopher Arnsfeldt Hansen, and Alexandros Hollander. And so first I'll briefly introduce this complexity class FixP, and then I'll discuss the main contribution of the paper, which is the construction of this so-called pseudogate for doing convex optimization in FixP circuits. And then lastly, I'll show a couple of applications of this pseudogate. Okay. So the class FixP is based on a theorem of Bauer called Bauer's fixed point theorem, which states that any continuous map from a convex compact set to itself has some fixed point. And examples of things that can be described as fixed points of such functions include, for instance, equilibria in finite games, which we will also, which I'll use in an example later. And so, as Sami and Yanakakis then introduced this complexity class FixP to basically capture search problems that where the solutions can be described as power fixed points, and the instances of a defining fixed point problem or FixP problem are circuits, or the instances of such problems are circuits using the following gates, so plus and multiplication and division and maximization gates. And this circuit then should then define some function from the hypercube to itself, and then a solution to this instance is then a fixed point of the function that the circuit defines. So this is a sort of standard problem in this FixP class, and then it is closed under SL reductions. And this means that a problem is in the class FixP if, given an instance of the problem, you can construct some circuit such that the fixed points of these circuits are solutions to the original problem. And then you should also be able to, given some fixed point of this circuit that you have constructed, you should be able to get a solution to the original problem in some using some simple map. So, for instance, it could be a projection map onto some of the coordinates of the input of the circuits. Okay, so now I'll describe this pseudogate for optimization. So, in many FixP membership results, it would be quite easy to show the result if we had access to some gate that could, where given the input, we might want to solve some solve some linear program, for instance. However, we only have access to these plus and multiplication and division and maximization gate, and with these gates we cannot just make a circuit that can solve an LP, for instance. And this can be seen quite easily. However, one can then observe that in FixP membership results we need to reason about the fixed points of our circuit. So this gate that should be able to solve an LP actually only has to work when the entire circuit fixes some input. So therefore, instead of just trying to make this gate that just given some parameters based on the inputs solve some LP, the idea is that we add some extra variables, and then this pseudogate that we call it also has some extra output. And then basically the point of the pseudogate is that when the entire input is fixed by the circuit, then this output set from the pseudogate, that will be an optimal solution to the LP that we actually want to solve. Okay, so that's sort of the idea of the pseudogate, and now I'll move on to some applications of how we can use this. Okay. So the first example I want to go through is this example of finite normal form games that I mentioned earlier. So the finite normal form game, it consists of some players, say n players, and each player has some strategies. And then each player also has some payoff function, which gives a value to when all the agents have picked some strategy, then it gives some real value for the ith agent. And but we really want the players to be able to play mixed strategies. And this just means that any player is allowed to play every strategy with some all of his strategies with some probability. And then we can also extend this these maps UI to in the obvious way to get the expected payoff of the agent when he plays according to his distribution. And a Nash equilibrium that then consists of a mixed strategy for each of the players, such that no player will want to switch strategies when all the other players keep their strategies constant. So this is the problem. So the input, we get these UIs, and we get that's basically what we get as an input, and then we want to find such a Nash equilibrium. And one way to do this was basically given by one of so Nash proved that there always exists such a Nash equilibrium, and in one of his proofs he defined a function that whose fixed points are exactly these equilibria, and that is quite convenient, because then when he has already defined the function, and so the function is here in the middle of the page, you can see that you can make it with only maxes and pluses and division and multiplication. And so we already have that this problem of computing a Nash equilibrium that is definitely contained in FixP. And actually, Ezra and Yanakakis also showed hardness for this problem. So here it was quite easy to show membership, but Nash also gave a different proof which doesn't use, or which isn't based on Brouwer's fixed point theorem, and then it would be harder to show membership. But actually, instead of using this function defined by Nash, we can also use our optimization gate. And the point is just to let we want to define some circuits whose fixed points are these Nash equilibria. And so we'll just let our domain of the circuit be the product of these simplices over the strategies. And then we define the function as follows. So the ith coordinate of the ith coordinate of the function, that is a strategy profile for that's a mixed strategy for the ith player, and it is the mixed strategy that basically solves the following optimization program. And this optimization program asks to maximize the utility of the ith agent, given that all the other agents hold their strategies constant, such that now the point, so the point basically is now that if we have a fixed point, then we see that x1 is already so for instance, x1 is maximizes the utility of the first player, given that all the other players hold their strategies constants, and so on for all the other players. And therefore, if we have a fixed point, then no player will have an incentive to switch strategies, and therefore fixed points of this function will be Nash equilibria. And so we get also the theorem that computing an equilibrium that is FixP complete also for concave in player games. So before I didn't mention it, but this theorem of Nash only works for when the utilities are basically linear. But our optimization gate also works when the utilities are concave. So we get this result. Okay, so now I'll move on to markets and Arrow-Debreu market. So what does it consist of? So an Arrow-Debreu market consists of some commodities. So we have a set of commodities, we have a set of firms, and these firms can each have some set of production plans. So that's what they can produce and how much they produce of each commodity and how much they use of each commodity. And then there's a set of consumers, and the consumers has a set of consumption vectors, so what they demand of the goods, and they have some shares in each of the firm, they have some utility function, and then they have also some initial endowments, so that's how much they have of all the resources. Okay. And now in an Arrow-Debreu model or market, we want to find an equilibrium, and this is just a tuple of consumption vectors, so consumption vectors for each of the consumers. It's a list of production plans for each of the firms, and then it's a price vector, so a pricing of all the goods. And they should satisfy a bunch of things. So for instance, they should satisfy, so for each of the firms, yj star should be maximizing how much the the payoff of this production plan. And for each of the agent, xi star should maximize the utility of the ith agent subject to some budget constraints. And then the fourth condition says that it basically says that the supply meets demand. So the supply, that is the initial endowments and how much is produced, and the demand is the sum of the consumption vectors. And therefore, z star is less than 0. That says exactly that there is enough stuff being produced, so the consumers can demand so much. Okay, so anyways, this is an equilibrium, and we can already see here, for instance, from condition 1 and condition 2, we have to solve some, we have to do some optimizations. Okay, and just some previous work. So there has been some previous results. So Arrow and DeBrew, they showed that under some certain conditions, an equilibrium is guaranteed to exist. And we also have some complexity results. So Chen, Paparas, and Yanakakis, they show that they show membership, fixed P membership for markets with so-called CES utilities and no production. And yeah, so they basically use that they have some closed formula for the consumption vectors in this case. And Gargmeta and Basirani, they showed fixed P membership of markets with another type of utilities. Okay, so yeah, so I'll just briefly go through the membership results. So we construct a circuit, and the domain should just be the product of the consumption sets, of the production sets, and of this 0, 1 to the L. That's the prices of all the items. And then when we have some input, we send it to some output, and then the ith output, that's just obtained as the solution to the following maximization problem. And this maximization problem exactly says that if we are in a fixed point, then xi will be equal to xi bar. And that says that xi already maximizes the utility of the ith agent subject to this budget constraint. And this is exactly, I think it was the second condition of the requirements of being an equilibrium. Okay. And similar, so we can solve some different optimization problems to ensure, for instance, that these production plans are also optimal, and so on. Okay, so that's what I want to say about the Arrow-DeBrew markets. And then finally, I want to come to a problem where the optimization part is perhaps a bit less obvious. And that is the problem of finding an envy-free cake cutting. So in this problem, we have some cake that is modeled by the 0-1 interval, and we want to divide it among n people, and by cutting it into n pieces, and therefore any division can be modeled by some point in the simplex, where each coordinate says so the ith coordinate of the point in the simplex gives the length of the ith piece of cake. And then the agents have some utilities uij, and uij is the utility of agent I for the jth piece of the cake. And then we have some assumption on these utilities, but I won't really get into that. And yeah, so the task is to find a division such that there is a permutation, such that when pi I is assigned to agent I, then he will value this piece more than any other piece of cake. Okay, and of previous work, there has been, well, Stromquist showed the existence of such an envy-free division, and then Su gave Simmons gave a proof that is in a paper of Su based on Sperner's lemma. And based on this proof, Denki and Saberi showed PPAD membership of the approximate problem, which is basically finding a division such that this inequality holds for some epsilon. And but there was no results of about the exact problem, but we show that the exact problem is actually complete for the class fixed P. So how can we use the upgate to show fixed P membership? So the main point just is that the first thing to notice is that any division in the simplex gives a bipartite graph as follows. So if we have the point a quarter, a half, then we get the following division of the cake that I've tried to draw here. And then here there are three agents A, B, and C. And now what we do is just we draw lines, or we draw edges between the players and the pieces that they prefer. So here player A will prefer the red and the blue piece, and B will prefer the green piece. And then what's the main point? The main point is that this division is envy-free if and only if there's a bipartite or a perfect matching in this graph. So how can we use our upgate to check if there's a perfect matching? So basically we define a circuit whose input is consists of a division. Then it consists of the capacities of all these edges. So we consider the complete graph, and then we have some capacities on each of the edges. And then the last part of the domain is the flow of all these edges. And so in a fixed point, we want that basically that the capacity should only be larger than 0 on the edges that should actually be there. So there should be some capacity on the edges from A to the red one and A to the blue one, but not from A to the green one. And we can ensure this by solving the following this maximization problem, because here we just maximize the sum of Zij times Uijx, subject to this constraint that the sum should be 1 and Z should always be non-negative. And then the only Zij's that will be positive, those are the one for which Uij is maximal. And yeah, that is exactly what we want, because then when we are in a fixed point, then this says that the Zij is only positive if the utility is actually maximal for that agent. Okay, and so this is a way to find all the capacities in this graph, and in a similar way we can find a flow such that the flow is the max flow just by maximizing all the sum of all the flows out of the agents. And then when we have this max flow, then we want to change the division. And the way we change the division is basically if there is some piece where the flow into it is less than 1, then we want to increase the size of that piece. And that is basically what this map does here. So it sends xj to xj plus rj and then divided by some normalization term, where rk is basically 1 minus the flow into this into the kth piece. Okay. And yeah, so then it requires some work, but then one can show when we define the map in this way, then any fixed point will correspond to x being an envy-free division. And so we get the membership result, the membership of the following completeness result of exact envy-free cake cutting. Okay. Thanks for listening.